Okay, so I'll tell you a little bit about what we are doing at ING on zero knowledges, and focusing on some applications and some comparisons and challenges that we faced. So, as we know, working with blockchain raises some privacy problems, and ING has a blockchain team, and they were worried with those privacy issues. And there are some possible ways to solve those issues without zero knowledge. For example, we can use trusted execution environments, SGX, HSMs, and some kind of special hardware to solve those kind of problems. And also there are the possibilities of using private channels, but those ideas are not the perfect solution for the problem. For example, SGX has many vulnerabilities known, so we decided to start exploring zero-knowledge proofs, which seems to be the ideal solution. The motivation is using zero-knowledge to solve privacy issues on DLT, but there are other applications in the bank that could benefit from zero-knowledge proofs. For example, we can mention for asset transfer, identity management, anonymous credentials, and in particular, auctions and procurement seems to be a nice application for zero-knowledge proofs. And blockchain is interesting because it allows transparency and automation using smart contracts, but then we have the problem of the privacy of the input parameters of the smart contract, so the holy grail would be to construct private smart contracts. So zero-knowledge proofs could be used in that context. And another application would be a cryptocurrency exchange, which seems to be a nice application. It's not the current focus, but maybe in the near future could be a focus for our team. So here we have the executive version of Alice and Bob. And they are trying to have a conversation, and Alice wants to prove and convince Bob that some property is true. So we have the usual properties like completeness and soundness and zero knowledge. I'm not going to give the details because I think everybody knows these details here. But our desiderata is to achieve those goals, and we want to have a non-interactive protocol using Fiat-Shamir transformation. We want to have actually a proof of knowledge. We are not dealing with NP-complete problems, NP-hard problems, or something like that, which have hard solutions. Actually, we're dealing with easy problems, like range proofs. So we want to convince Bob, Alice wants to convince Bob that she knows a secret which belongs to a certain interval. And so, for example, in order to prove she is over 18, she wants to prove that her age is between 18 and 200, for example. So it's easy to find all the numbers between 18 and 200. So it's proof of knowledge, because it's hard to distinguish between her secret and all the other possibilities in this interval. So we have the indistinguishability of those secrets. And we want to have an efficient construction, obviously. And lastly, we want to have a non-trusted setup, and maybe in the near future, a post-quantum construction for this problem. As I told you, the range proof allows you to prove that some secret is between two numbers, and we don't want to reveal any information about the secret. And so there are some categories to solve this problem. There's a paper from 2001 from Boudot using square decomposition. And this was our implementation, I think 2 years ago. And then we decided to implement a scheme from 2008, which is also capable of doing set membership. So instead of only doing range proofs, we can prove that our secret is an element from a set. It's more generic than range proofs, so we can use it with a generic set and not only a continuous interval of integer numbers. Another possible solution to obtain a range proof is called multi-base decomposition. We didn't implement this solution. And last option was a recent proposal called bullet proofs. And we saw this paper and decided to implement it, to experiment with this and acquire the knowledge and understand how to construct those solutions. So bullet proofs is an efficient solution for zero-knowledge range proof, and it was designed for DLT, and it allows to compute generic statements as in ZK snarks and ZK starks, so it's also very flexible and powerful. It's not restricted only for range proofs, and it's very interesting that it's not dependent on a trusted setup. This is important because if there is a trusted setup, then it would be possible to generate fake proofs, and this may be catastrophic in many scenarios. So we don't want to have this trusted setup, and we decided to implement bullet proofs because of this requirement. And since we want to avoid this requirement, we searched for papers, and it's possible to avoid this using multi-party computation, but actually we decided to simply choose a protocol which is not dependent on a trusted setup. So some applications for this kind of problems is, for example, in the context of DLT, we have this paper describing confidential transactions where we want to transfer money from one party to another, but we want to hide the participants and the amount of money being transferred. So it's possible to solve this problem, use range proofs and other techniques, but range proofs is a key element in this solution. And Mimble-Wimble is a paper that describes a way to optimize this construction of confidential transactions. And using bullet proofs, it's possible to do this Mimble-Wimble solution more efficient. It's like a perfect fit. It's much more efficient to use bullet proofs to construct this Mimble-Wimble and the confidential transactions than other range proofs. And also another application which seems to be very interesting for exchanges is provisions, where you have an exchange and you want to convince your clients that you have enough balance to pay all the clients if the clients decide to withdraw their money at once at the same moment. Then the exchange is capable of proving in a zero-knowledge way that it has enough funds to pay the clients. And not only considering DLT, but more generically, we have other applications for zero-knowledge proofs. For example, we have this Know Your Customer, which is related to identity management. So it's very interesting to use in that context. And we have also the possibility of using zero-knowledge proofs to solve problems related to regulation, like anti-money laundering. So we can validate that you are doing business with a company that is not under some kind of sanction. Also, we can think about this solution in a generic way and have a reputation management. So you can use the set membership protocol to basically have a white list or a black list, and you prove that you are not doing business with someone in the black list, for example. Another way to use zero-knowledge proof would be to have a provenance. So you can track the history of a good For example, you are not buying wood from deforestation, for example, or any other kind of provenance guarantee that you want to have without disclosing more information than necessary. Another topic which seems to be very interesting for banking is Common Reporting Standard, the CRS, where you have a dynamic way to exchange financial information between institutions. And since this is a dynamic solution, we can't have a static solution to this problem. We need something like ZKProof, where we can provide a zero-knowledge proof for generic statements. So this requires something like ZK-SNARKs or maybe bulletproofs. And more specifically, we can use zero knowledge for electronic voting and electronic auctions. Here I will give you some comparison between the implementations. For example, the proof size, we have that bulletproofs is more efficient, have a smaller proof size. And I'm using here a window. So if we have a very big secret, bulletproofs will still be the best solution. But for the prover complexity, for example, we have that this multi-base implementation is better for small secrets, and bulletproofs is better after some point. And we have that the square decomposition is constant, so at some point, bulletproofs is going to be worse than bulletproofs. Well, bulletproofs is going to be worse than the square decomposition, because square decomposition is constant, but it will only be better for very big secrets and ranges. And for the verifier complexity, we have a similar situation. Bulletproofs is better for small secrets and medium-sized secrets, but for very, very big secrets, we have that the square decomposition at some point will be better. Some timing information for the implementation. The Budo was implemented 2 years ago. The signature-based scheme, which is the CCS paper from Kamenisch et al., is the second line. Our implementation is the third line, and the last line is the implementation from the authors of bulletproofs. So we can see that with bulletproofs, it's possible to batch the verification. So the verification is really very efficient using bulletproofs, but we didn't implement the optimizations. We implement just the basics, but we didn't implement this batching technique. Maybe it will be implemented in the near future, but we implemented bulletproofs as a proof of concept to understand how difficult it would be. Some challenges, we want to understand how mature this technology is, because although it is an old line of research, it's kind of new for the industry. So it's necessary to get a mature solution for the industry and not only for the research. It's necessary to have a regulation to accept those kind of zero-knowledge proofs by regulation. So the standardization workshop is very important, because it will be the necessary steps towards this regulation. And some thoughts about trust. It's very interesting, this discussion, because blockchain allows to avoid the trust between parties. It's a good solution regarding trust. But then if we use zero-knowledge proofs to protect privacy, then if we use a trusted setup, then we are back to the original problem. We have a trusted party. But first of all, what's trust? Because we have the trust according to technology, according to business, or according to law. So there are different concepts of trust. We can trust on the setup of the scheme, as I was telling you. But there is also another point, which is the trust on the commitment. Since, for example, range proofs is an easy problem, everybody can compute all the numbers between two numbers. So if you were responsible for generating your own commitment, you could lie. You cannot. I would not trust you if you give me a commitment about an easy problem, because you could lie. You could use any possible secret. So I need someone else to attest this information and commit on behalf of me, so that I can use later this commitment to prove to different parties generic properties. So this is a topic that will be discussed here. It's one of the line of the proposals to the workshop. So this commitment, then proof. It's interesting because you have the commitment in the first step, then you can use it to generate proofs for different intervals or different instantiations of the problem. So these are two different ways to have trusted a trusted party in using zero-knowledge proofs. The first one, the trusted setup is catastrophic in many scenarios. And the second one, the trust in the commitment, is not that problematic. For example, in the case of a range proof for my age, if I want to prove that I am over 18, I could lie. But for example, in the case of auctions, I am going to bid, so I have it's not necessary to have a trusted party to attest my bid. I can compute my own commitment. So in many applications, and I can commit myself, but in other applications, it's not possible. You need a trusted party to attest your information and compute the commitment on behalf of you. So some final remarks here. We understand that zero-knowledge proof is going to be an important way to solve the privacy issues, and not only on blockchain, but also for many other problems like cloud computing, databases. And the standardization and regulation is very important, because we, as a bank, we are very regulated, so there is regulation everywhere. So we need to have this regulation and this standard in order to put this kind of solution to work in production. We are experimenting with many protocols, implementing, doing proof of concepts, but if we want to use that in practice, we need to have regulation to make it real. So as next steps, we want to implement, for example, the optimizations in bulletproofs, like using multi-exponentiation and the aggregation technique. Also, we could implement the beyond range proofs. I mean, using bulletproofs to have more than just range proofs, because it's possible to have, for example, set membership and other gadgets using bulletproofs. And when compared to ZK snarks, it seems that bulletproofs is more appropriate for those gadgets, and it seems that it's not that appropriate for a generic problem. This is my feeling, but that's my current conclusion. I think that bulletproofs is better for simple problems like range proofs and set membership and those kind of gadgets. And we can explore concrete applications in the near future. We are talking to different initiatives in the bank because there are many ways to use this technology, and we are having many meetings to discover how to fit the solution to the problems. It's not an easy task because those solutions in the bank, they are already working in practice in some way. So there is a current implementation that's not using zero knowledge, but it's working in practice. And in general, they are using a trusted party. So, okay, we can remove this trusted party or minimize trust, but this means that we are going to change something in the solution, and this involves big companies, so it's a process that is not so simple. But if we have a mature solution, very efficient, zero knowledge construction, then we can convince the parties that it would be good for everybody. And lastly, a topic that is more related to research is a post-quantum zero knowledge proof. There's a recent paper from Chris Piker proposing a solution to this problem, which is very nice. Probably it can be part of our next steps as a research, because we have our business part at the implementation and open sourcing these implementations, these proof of concepts, but we also are worried with research. So we are starting to form a group of research, and we hired a cryptographer, which is here in the audience, and it's very good to know that we have this traction in the field, and zero knowledge is gaining so much attention. And here, some references, and that's it. Questions?
Okay. Are there any questions?
Yeah, just I can speak loud. So maybe I missed it, but can you tell a use case, a real-world use case that ING, where ING sees zero knowledge as a differentiator? Because I didn't get it.
For example, in practice, in the Netherlands, there is an institution that knows if someone is, some people need to pay a debt, and the municipality knows the financial situation of this person. So those are two different institutions, and there is a privacy issue. The municipality cannot open the financial situation of the person to the other institution, but this can be solved with zero knowledge proof. For example, you can use a zero knowledge proof to show that some person has enough money to pay the debt. So it uses a zero knowledge proof to show this property to the other institution, so the other institution can go to the person and say, you need to pay. This is, since we are in the exploration phase, we have some small applications being constructed. Those applications are also proof of concept. There is nothing in production, but there are many conversations, for example, to use, for example, provenance. There's a project where we can maybe use zero knowledge to prove the provenance. We know that the good, the whole history of the good is okay, is not problematic in some way, but this is very generic for now. We are exploring many possible applications, but we are not solving the problems concretely now, but we are choosing which problem we are going to face and focus and prioritize next.
Do you have any idea of the business model that you can open with that?
Business model, we are discussing the business model. It depends on the application. For now, we are just exploring, so we don't have a business model established yet.
There's a question here.
Hey, so one of your earlier slides said that it was the most efficient for blockchain specifically. So my question is, when you're trying to articulate this in ING with IT and enterprise architecture, is there an alternative that they propose to you that's non-blockchain, that's more efficient, more private, more scalable? What are you hearing that's non-blockchain that would be used as opposed to going the DLT ZKP route?
Bulletproofs is very efficient indeed. It was designed for DLT, but maybe in some specific context, ZK snarks or some flavor of ZK snarks, because we talk about ZK snarks as if it was one single protocol, but there are many flavors. For example, we cannot say that ZK snarks is dependent on a trusted setup. Ligero, for example, is not dependent on a trusted setup. So it depends.
But is there a non-DLT, non-ZK snarks option that your organization could go down that pathway that would reach the same kind of ultimate?
For example, cloud computing, because as a bank we are delegating computation to cloud.
Sorry guys, I just wanna, let's take it offline.
Yes,
Thanks.
we can talk offline.
Thank you. Let's thank the speaker.